Hello, welcome to the Mathematics Notation Unit. In this unit, we are going to explore a few mathematical symbols that will be used throughout the module. So let's start with the symbols found in predicate logic. The most important are the following. To say that in mathematics there exists an element, it doesn't have to be unique. Satisfying a certain property, it is represented by the symbol you see on the screen, an E in reverse, existential quantifier. When we want to also say that it exists and is also unique to the element, then we use the symbol that is an E in reverse with an exclamation mark. Then, in addition, to indicate that a particular property holds true for all elements, the symbol used is an A, universal quantifier, which resembles an upside-down A with a horizontal line. It is read as for everything. Next, we will see an example in which we will use some of these symbols. It is also important in mathematical discourse to articulate the concept of all elements such that they satisfy a certain property, in addition to existence and for all. Well, the such that concept can be represented with a horizontal bar, a slightly inclined bar, or two colons. Let's explore an example to illustrate how these symbols can be employed. We want to express that the equation x plus 2 equals 3 possesses a unique solution. It is evident that there is a unique solution. Upon examination, we find that x equals 1 satisfies the equation as 1 plus 2 equals 3, confirming the uniqueness of the solution. Well, how would we express that in mathematical language? We can state that what we intend to convey is the existence of an x, such that it satisfies the equation. In other words, x meets the equation. There is an x such that x plus 2 equals 3. If we use the notation we discussed earlier, we would write it as follows. It exists an x such that x plus 2 is equal to 3. In fact, we know that it exists, and x is equal to 1. Additionally, we could have included the uniqueness aspect, as there is a unique element x for which x plus 2 equals 3. Another example involving for all is the well-known identity x equals x. Then, how do we write that for all x is fulfilled, that x is equal to x? It could be, as we can see on the screen, that as for all x, x is equal to x. Note that the symbol for everything is placed before the x, and it is read as for everything x. Let's briefly delve into partial orders. This unit assumes a foundational understanding of concepts covered earlier. Partial orders are a way to compare two elements, determining which is smaller or greater than the other. Notice the symbol, which resembles a left-pointing vertex, signifies less than. When we place an element in front and behind it, as in the example, it means A is less than B. If we reverse it, it indicates that A is greater than B. Pay attention to the direction of the vertex. It indicates which value is smaller. In the first case, A is less than B, simply denoting A less than B. In the second case, A is greater than B. An example of this is that 2 is less than 3. And in the second example, 5 is greater than 4. This concept can be further refined. Sometimes we can include less than or equal to, indicated by a vertex with a horizontal line beneath it. In that case, it signifies less than or equal to, allowing for the possibility that A is equal to B. In the example, we observe that A is less than or equal to B. Since we don't have specific values for A and B, we can infer that A is either smaller or equal to B. The same principle applies to greater or equal. Note that the vertex points to the right. In this case, we would interpret it as A is greater than or equal to B. The value of A, which is initially unknown, could be either greater than B or equal to B. Another important aspect we'll cover in these modules is the part related to set theory. There is a dedicated unit that focuses solely on sets and set theory, where these symbols are explained in greater detail than we will cover here. However, I'd like to take this opportunity to briefly introduce the main symbols we'll use in set theory. Observe that when we have a set and an element that is a member of that set, we represent it as x belongs to A, as shown on the screen. X belongs to A. The symbol is a slightly curved E, with x placed to the left and the set to which it belongs on the right. It can also be written in the reverse order, but using the symbol E on the other side. When we want to express that an element does not belong to a set, we simply add a bar across the previous symbol, resulting in x does not belong to A. Regarding set inclusion, it's important to note that sets can be included in others. For a more in-depth explanation, please refer to the unit dedicated to sets. To express that one set is contained within another, we use a symbol resembling a horizontal U, with the set to be contained on the left and the containing set on the right. For instance, when A is contained within B, it would be written like this. A is contained in B, it means that A is a subset of B. Well, if we add a horizontal bar beneath it, it indicates that it can be contained or it can be equal. So if we write A is contained in B, it would mean that A is a subset of B, or A is equal to B. These are indeed the fundamental elements for constructing mathematical expressions. We have covered the concepts of existence, uniqueness, universal quantification, as well as relationships of inclusion between sets and ordering relationships among real and rational numbers, among others. I hope this unit has been helpful. See you in the next ones. Thank you very much.